Okay, great. So our last speaker of the day is Ryan O'Donnell, and he's going to scare us.
Yeah, hold on. There's supposed to be sound. There we go. I'm supposed to scare you with this talk, yeah. I actually didn't even want to give a talk about this topic, but I was asked to give this talk, so I got it for you here. Yeah, also let me say, Mark and Alex, I know you're watching on the live stream, so thanks, but remember you got to go to bath in bed after this is over. Right, so as I said, I kind of apologize for being here because it's not everybody's favorite topic, and like I guess I'm up here just to scold you about these things, but I'll try to make it a little bit fun, throw in some fun facts in the course of the next half hour on this subject. Okay, so here's some statements that I collected from some published papers. I'll read them to you. So this says the SOS hierarchy can be solved in time n to the order d for degree parameter d. The SOS parameter with algorithm with parameter L takes n to the order L time to run. This one says if a degree d SOS proof exists, it can be found in time n to the order d. Actually, I wrote that one. Actually, I wrote a couple of these. Right, so after reading all those statements, you'd be forgiven for thinking that like degree d solutions, SOS solutions, can be computed in n to the order d time by an STP. But that statement is false. Okay, strictly speaking, I have to say like it's not known to be true, but it's probably false. But some people say yes, I know, because there's the approximation, right? You can't compute them exactly, maybe up to some like additive exponentially small error. You can do it with STP. But this one is also false. And in fact, it's still false thanks to the work of Ben and Prasad. Even if all the variables are constrained to be Boolean in your SOS program, just plus or minus 1. So that looks a little unnerving. So let's back up the truck before we even get to there. And I'm going to really insult your intelligence now by talking about linear programming. So let's start at the very beginning. So the linear programming feasibility problem. You're given A, you're given B. These are rational matrices and vectors. And K is the set of points where AX is less than or equal to B. And you want to decide, is this a non-empty set or not? OK, so is this problem in P? In other words, is this problem solvable like on a Turing machine in time that's polynomial in the size of the input? Well, we have to think about what is the size of the input. And there's bit complexity, OK? So these are all rational numbers. And it's traditional to write L for the number of bits in the input. And I'm using this angle bracket notation for like literally the number of bits you need to write down this mathematical object, this matrix of rationals and this vector of rationals. Good, so let me store that up here. And let's ask the question again. So is this problem solvable in polynomial time? And in fact, before we even get there, I know you guys all know the answer. But let's first ask if this problem is in NP. And at first, you're like, of course it's in NP, right? I mean, you just give the point x, that's the witness for it being non-empty. But of course, it's not quite as easy as that, right? So it's not immediately obvious. Because, for example, like the prover has to give you the points. And it has to write it down. So you have to first ask yourself, well, if this is not empty, is there a rational point in this polytope? And furthermore, it's not enough for there to be a rational point in it, right? You have to write it down with polynomially many bits. So you would like to know if it's not empty, does it necessarily contain a point x whose magnitude is at most exponential in L? That's OK. That means you can write it down with polynomially many bits. All right, now, so I know you all know the answers to these questions are yes, and you can prove it by very elementary linear algebra. But OK, just wanted to say this, like not immediately obvious that this problem is even in NP. OK, so we know this fact. Before we get back to P, let me stall a little by asking, is this problem in co-NP? And of course, the answer to this question is also yes, because of LP duality. That's nice. So we know that given K, you can mechanically in polynomial time transform it to another LP problem, K star, basically the same size, such that K star is feasible if and only if K is infeasible. OK, so then you can thereby prove that it's empty by exhibiting a feasible point for K star. OK, great. So we have a problem that's in NP. It's also in co-NP. So then finally, this is historically, I guess, how it happened. We can ask, is it in P? And yes, it's in P. You all know this. This is proved by Kachian. And then the proof details were filled in the same year by Gotts and Lovas, thanks to the ellipsoid algorithm. So I want to remind you a little bit about the ellipsoid algorithm, how it works, and why this problem is in P. So the ellipsoid algorithm takes as input two radii. These are going to be major players in the talk, big R and little r. And it also takes as input a convex set K, but it doesn't have to even necessarily be given explicitly, as you know. It's enough for it to be given by a so-called separation oracle. And what's a separation oracle? It's like some algorithm where if you give it a point, x0, the oracle either tells you, yes, that point is in K, or it gives you back, if x is not in this convex set, it gives you back a half space that separates K from x0. And of course, if you have this polytope ax less than or equal to b in your hands, you can easily implement this oracle for yourself in polynomial time. But really, the ellipsoid algorithm only interacts with the polytope through this oracle. OK, so those are the inputs. But there's also an assumption. And I know you all know all this stuff, but let me go over it anyway. That either the polytope is empty, or it has two properties. First, it's contained in a giant ball of radius big R centered at the origin. And it contains at least some ball of radius little r. OK, so it's not just non-empty, but like actually contains a little ball. So under these assumptions, with these inputs, the ellipsoid algorithm either outputs a point in K, or it outputs correctly that K is empty. Again, we can remember how this algorithm works. You start out with some polytope K. By assumption, it contains at least some little ball of radius little r. And the algorithm knows it's inside this big ball of radius big R. And OK, the ellipsoid algorithm, it just starts querying points. So it queries the center of this ellipsoid and says, is this in K or not? And in this case, it gets back no, and it gets back a separating hyperplane. So the ellipsoid algorithm puts the smallest ellipsoid it can around this region that supposedly contains K. And it proceeds. It's easy to show geometrically that the volume goes down by a factor of like 1 minus 1 over n. So we're making good progress. You query the center again. It just barely misses. You get another separating hyperplane. You put another ellipsoid around this region. And in this case, then you query the center again, and you found your point in K. Or alternatively, like maybe K actually didn't exist at all. It was empty. So the ellipsoid algorithm will query this point and get back some. This is technically a separating hyperplane for the empty set. And it'll keep going. And the ellipsoid keeps shrinking and shrinking in the case where K is empty. Until the algorithm realizes this ellipsoid is too small to contain a ball of radius little r. And now it knows by assumption it can stop that K must actually be empty. OK, so that's ellipsoid. And the running time of it is polynomial in n, and the number of bits to write down big R, and the number of bits to write down little r, and L, which is the max bit size that the oracle answered, the answers that the oracle gives you. OK, so this is all fine. Good. OK, so right. So now to apply this in case of LPs, again, it's not totally immediate, but it's not too hard to show that using capital R being exponential in L suffices, which is OK. The LP doesn't actually have to be contained in like a giant ball of radius R, because it could be unbounded, for example, but you can get around that quite easily. And it's also actually typically the case with LPs that like they don't contain a ball of radius little r, because usually they have like some equality constraint and they're not even full dimensional. But of course, you all know like a little wiggling, you can get around this too. And some little tricks, it's enough to show. You can show that you can reduce to the case where r is exponentially small in L. And that's also OK. Great. So this is all some easy stuff. Right. So not only does the ellipsoid algorithm solve the LP feasibility time and polynomial time, you also know that it like has all these bonus features. You can find vertices, you can optimize linear functions, detect unboundedness in polynomial time. And actually, this is a cool extra bonus too. Since the ellipsoid algorithm only interacts with the LP through a separation oracle, actually, you don't even need to have the polytope in front of you. And the number of inequalities can be anything, m, as long as you have a polynomial time separation oracle for your polytope. OK, and that's very useful in combinatorial optimization to optimize over these polytopes that you only sort of implicitly have access to. So this is great. Everything about LPs looks good. So to summarize, if you ask yourself, is everything I think about, everything I thought I knew about polynomial time LP solvability true?
The answer is it is in fact true.
So everything is true. Everything you thought you knew, true. It's fine. That's very quiet, but it's supposed to be dramatic. I'll make the next one louder. Wait, OK. OK, although this is not really relevant for the talk, but I like this fun fact, so I'll throw this out here for you. This double bonus that gets used a lot in optimization, this is actually pretty hard to prove. Like I kind of explained it to you, but it's not as easy as that. So this actually, to prove this, requires the theory of simultaneous Diophantine approximation and like the LLL lattice basis reduction algorithm. I think that's half the reason like Lovász was interested in this lattice basis stuff. So this thing that I always thought was like immediate from ellipsoid, it's actually very difficult to prove. But it's still true.
Why is that?
Why? It's an interesting question. It's because like what if the polytope is not full dimensional and like you have a very bad separation oracle that keeps giving you parallel separating hyperplanes that split you. At some point you have to realize that it's low dimensional even though you don't have K and like jump into a low dimensional subspace. And some Diophantine.
Sorry, so here the assumption that you lift the little r and big R thing is not, you don't make the little r and big R assumption.
Right. So in the general case, when you just have that, it's a little bit embarrassing too. When you just have the separation oracle, you just assume that you don't necessarily have the big R and the little r, but you assume the separation oracle's answers. You're willing to run in time polynomial in the number of bits they return. Okay, so that's LPs. Everything is fine. But interesting, actually. OK, so now we have to move up to STPs. OK, so as you know, an STP is just literally an LP, except that the number of variables is like a perfect square, and you think of the variables as being arranged into a matrix, and you always have this extra condition that the matrix is PSD. And the fact that a matrix is PSD is just equivalent to all these linear constraints on the x variables. One for every, well, real vector y, you get a linear inequality on the x's. So that's actually kind of great. It's like the situation we were just talking about, where you have an LP. OK, it's got lots of inequalities, but there's a polynomial time separation oracle. That's no problem. If I give you a rational matrix X, you can, in polynomial time, exactly decide if it's PSD. That's not so easy to prove, but it's been known for a long time. So great. So it looks like we're done. We got the separation oracle. So we should be able to solve semi-different programs in polynomial time.
It is a lie.
Sorry. Yeah. Unfortunately, it's not quite as easy as that. Because you go to use the ellipsoid algorithm, and you have a separation oracle. But there's these r's, the big R and the little r. And this assumption that the STP is either infeasible or it's contained in a big ball and contains a small ball. And basically, there's no reason for either of these assumptions to be true.
Right.
Yep.
I keep forgetting. So when you need to check whether a matrix is PSD, you need to be able to compute square roots somewhere?
You can do it like all over the rationals exactly. I mean, it's not. You shouldn't just like try to find a small eigenvalue or anything. Basically, you attempt to do the Cholesky decomposition and see if it succeeds or not.
That doesn't require square roots. I'm probably
no. You'll actually even see later how to do it in polynomial time. But yeah, you do it entirely over the rationals. It's totally exact, yeah. But you have to think about it, yeah. OK, so for the little r problem, these are all facts that I know you all know. Like, there are feasible rational STPs where the only feasible points in them are irrational. And for the big R problem, it's well known, there's feasible STPs where they're feasible, but the only feasible points are exponentially far away from the origin. Well, doubly exponentially far away from the origin. And therefore, writing down the closest feasible point still takes exponentially many bits. So, I mean, these points together, these facts together, make it even a drag for, asking yourself, is this problem even in NP? And it's unknown if it's in NP. In fact, I guess the experts believe it's not in NP. Here's another fun fact, though, here. It's in co-NP if and only if it's in NP, because of duality. And this is a fact that I personally did not know until recently, but there's an exact STP duality theorem due to Ramana. There's like no interior feasible points. There's no Slater conditions. It just literally transforms it into another STP, which is feasible if and only if the original guy is feasible. So I was interested to learn that. So we know the problem is in NP if and only if it's in co-NP, but probably it's in neither. So then you may say, whoa, is this problem even decidable? And yes, it's decidable by reduction to the existential theory of the reals. But that's basically the best thing we know. Not that it's just decidable, but by using this fact. So it's also nice for SOS lovers that there's a great paper of these heroes, Grigoriev and Vorobjov, in '88. They showed that this existential theory of the reals is in exp. And then a similar time, Canny showed this in p-space. So the semi-definite program feasibility problem is in p-space. And that's the best complexity upper bound we know. Again, I apologize if you know all this stuff, but these are things that I myself only discovered kind of recently. So thought I'd bring it up. OK, but we're here to talk about SOS. You might say, what about just sum of squares testing? So here the problem is you're given a multivariate polynomial over the rationals, and you want to know if it's a sum of squares. And this is a special case of SDP feasibility testing. For this particular polynomial right here, I just wrote it down. If you want to know if it's SOS, it's literally if and only if. I mean, we saw this in the previous talk, for example, or 2 talks ago. Some matrix M is PSD such that this M satisfies some equality constraints. Whether or not this SDP is feasible is equivalent to asking whether this polynomial is SOS. So it's a special case of SOS feasibility. But as far as I know, it's not known to be any easier. So in fact, the best upper bound on deciding this problem that I know is p-space. That's kind of a drag, too. And we can just review why it may still be a problem. So there's this little r problem. First of all, this SDP is never full dimensional at all, because it has all these equalities to get the constraints, the coefficients right. So it's never going to contain a ball of radius little r. Also, it's a related issue. This particular polynomial right here is SOS over the reals, but it's not SOS over the rationals. So that's proved recently. And again, it's going to kind of make it tough to imagine that this problem is in NP. I mean, it could be, but this is some kind of barrier to it. And there's also the big R problem. I actually personally don't know if this is an issue or not. Maybe somebody in this audience knows whether it's possible that a polynomial is a sum of squares, but there's no way to write it as a sum of squares using numbers that are not enormous. I don't know if that's known or not. So the big R problem could also be a fundamental barrier here, too.
No, I think you can bound it.
You can bound it. Okay.
That one should, I think.
OK, good. Yeah, I'm glad that.
What do you mean by that never? What do you mean by that never?
Never?
Of dimension?
Well, I mean,
For this example.
well, I mean, just whenever you cook up the SDP that looks like this, right? It has all these equalities, so it's not going to be a full dimensional.
But
The feasible region, if it exists, is not going to be a full dimensional region of.
No, but usually that's not what you mean when it's full. Even when you do LP, right? You don't say that it's full dimensional thing of the non-negative orthant. You want it to be full dimensional in the ambient subspace in which you slice.
in the relative interior.
Yeah, I mean, if you want to, I mean, just use ellipsoid out of the box, right? It's supposed to have a full dimensional little ball in it. So yeah, there's reductions to get around that in LP, and you can attempt some, I guess, reductions here to get around it. But
Yeah, in that form you would just parameterize the subspace. Right? I mean,
yeah. OK. Good. Yeah, so I'd be interested to hear about that. OK, but then you might say, well, I'm really an optimization person. It's not like I'm dying to know if it's exactly a sum of squares. Maybe I was just trying to certify that it was non-negative, and I wouldn't mind certifying that it's at least negative epsilon. That's cool to me. I'm not sure if that exactly makes sense by scale invariance. I mean, so anyway, let's recall the SOS method. Really dive into this question about, let's say, approximate sum of squares testing. So we've seen it many times, so I don't have to recall it too carefully. But the problem here is you're trying to maximize some polynomial subject to some polynomial equalities and some polynomial inequalities. And just assume that all these input polynomials are of really low degree, like 3 or something. And of course, this encodes lots of natural NP-complete problems. OK, so the SOS D method with parameter D is to try to certify that R is at most some number beta on the feasible region by writing it like this. We've seen this before. You want to write beta minus R in this sort of obviously manifestly positive way, where these A's and BI's and CI's, sorry, the A's and BI's are SOS. The CI's can be any polynomials. And if you can find such polynomials of degree at most D, then that certifies that R is at most beta on the feasible region. So that's how SOSD works. OK, and the existence of these polynomials is indeed an SDP feasibility problem of size n to the order D, so polynomial size of D is a constant. And let me even make our lives easier. Typically in optimization, you don't mind including, often don't mind including inequalities that keep everything bounded, like xi squared is at most 1 for all i's. This makes it compact. It makes everything nicer. So let's just always even assume this. OK, then there's some good news. The good news is that the little r problem in this scenario is no longer really a problem. OK, so basically, even though the SDP has all these equalities and so forth and inequalities, you can like fuzz the feasible region a little bit so that it contains like a small ball of radius r being like exponentially small. And then if you get back a fuzzy certificate that, oh, this is a little annoying that I used capital R here. Here I meant the polynomial, that the polynomial r is at most beta. Then you can fix it up to get like a genuine certificate that the polynomial is at most beta plus something that's exponentially small in this region. Yeah, this is using the compactness. And in optimization, that's probably enough for you. So that's fine. But the bad news is that the big R problem, it's a really unfortunate notation choice by me. The big R problem is still a problem. In particular, this is a very trivial thing I wrote down recently. There's a degree 2 instance of like an SOS optimization problem with these constraints, where even any approximately good certificate that like certifies the optimal value to like an additive 0.1 requires coefficients that are in the SOS certificate that are doubly exponentially large. Okay, so cannot be written down with polynomially many bits.
But what are the size of the coefficients in this degree 2 instance?
They're either all 0 and 1, or maybe they're between integers between 0 and n. So they're tiny. They're all 0 or 1 or 2, actually.
So you have these equations, these consistency equations, right? And for your notion, you still require that they are satisfied with equality?
Yeah. In the instance, yeah.
I would think if you drop that, you allow some approximation there, then you'll be safe.
Well, you can, that's OK. I mean, actually, you can fix, if they're not exactly satisfied as equalities, you can actually fix them up to be satisfied exactly as equalities. So in this compact case. So it's not that, yeah, somehow in this instance, it's not like satisfying the equalities exactly is the issue. It's just that like the only certificates really use like doubly exponentially large numbers.
That's a question.
Yeah.
Certificate of what degree? Is it for a particular degree?
That's a good question. Yeah, for a degree 2 certificate. So the point is that there exists a degree 2 certificate that this instance I wrote down has minimum. It's a minimization problem 0. But like any degree 2 certificate that certifies it's at least negative 0.1 requires these doubly exponentially large coefficients. And actually, in the follow-up paper by Prasad, he points out that actually in this particular thing I wrote down, there's a degree 4 certificate that's has small coefficients and gives a good bound. But then he gave like a worse example where like even if you go up to degree root n, like you can't get anything good. So this is in fact the bad news. So he gave like Ragaventra and Weiss gave like a much worse example for 2 reasons. One is even in the case where all the exact Boolean inequalities are included. So you're not just optimizing over a compact region, you're just optimizing literally over the discrete cube. And he gave some degree 2 instance. They gave some degree 2 instance where even to certify the true minimum to some constant additive error, you require doubly exponential coefficients, and that remains true even if you try to use up to degree, I think, root n.
You can do lower degree certificates. So at root n, you need exponentially large bit size.
Below root n, you need exponentially large bit size to get like any approximately correct certificate. Even though there exists like a perfect degree 2 certificate, but just the degree 2 certificate uses enormous numbers. Yeah.
So can this example be explained?
Well, the man is sitting right next to you, not in this short amount of time. But this example is literally, it's literally nothing more than taking like the very classical SDP example of like a feasible SDP that requires where all the feasible region requires like doubly exponential size, and basically massaging it into an SOS situation where this approximately situation still holds true. Actually, as Pablo pointed out to me, like any SDP feasibility problem at all can be viewed as like a degree 2 sum of squares problem modulo an ideal. So like as soon as you have like any bad thing happening in SDPs, it basically arguably is also happening for SOS. OK, so there's some good news. This is not all bad news. This is some good news. when these are the only constraints you have, the only constraints you have are Boolean equalities, so you're just optimizing a polynomial over the hypercube, then everything is OK. Okay, everything is OK. So like Gomez-Williamson Max-Cut algorithm, OK. And it's actually, this is one other fun fact I like to tell people. This fact that Gomez-Williamson was OK was proved by Delorme and Poljak in 1990, 4 years before the Gomez-Williamson paper. I love this paper. It's a great paper. So they proposed the degree 2 SOS certificate method for upper bounding the maximum cut in a graph. And then they're like, chapter 7, existence of a polynomial time algorithm. And they're like, they got the big R, the little r, they got it, it's all in here. The rationals, they're appealing to like the ellipsoid algorithm here. They're showing that like testing of a matrix's PSD can be done in polynomial time. Actually, they made a mistake here. They said that a matrix is PSD if all the principal minors are PSD, which is false, but it's close to being true. And these heroes back in 1980 actually correctly showed that this is the proof that you can test if a matrix is PSD in polynomial time right here. Yeah, so it's all fine. You can handle this case. So optimizing a polynomial over the discrete cube with the SOS method is OK. And again, these heroes, Rogov, Endro, and Weitz, showed some other OK cases in this recent paper. So like optimizing over the cube with these clique constraints is OK. So like everything that Sam and Aaron told you this morning is OK. And optimizing not over the discrete cube, but over the sphere is OK. So everything Vijay told you today is OK. And some other things, like if you want to like impose like a bisection constraint on the hypercube, so like you want to maximize over the middle Hamming layer of the hypercube, that's also OK. Even though actually like the Grobner basis for that is exponential size, you can get around it. It's OK. So there are some more cases where everything is fine. And roughly what they show, I mean, there's some things you have to check. You should check out the paper. But roughly they show when all the equalities that are implied by sort of the input equalities and inequalities, when all these implied equalities are easily derived in SOS, then everything is OK. But sometimes like the equalities and inequalities imply some other equalities, which for like non-obvious reasons. And that's the situation where we don't know things are all right. So in particular, like let's say you're in the context of Boolean CSPs, and instead of like trying to maximize an objective function subject to the Boolean constraints, you instead start trying out different values beta and asking, hey, is it feasible if I impose the constraint as an equality, objective equals beta? That's kind of a natural way to use optimization to try to approximately solve a CSP. And that one, we don't actually know how to do that in polynomial time. OK, so I'm basically done. And, just the summary of what we've talked about here is this. I mean, I love SOS. I'm not trying to scold you or anything. It's great. But just the only thing I want to say is like if your goal in life is to show that some problem is like literally in P on the Turing machine model, and you're using SOS, then OK, you have to take a little bit of care. Thanks.
Comment for Ryan.
Yeah.
That the Gomez-Williamson is fine in terms of bit sizes?
Louder.
Sorry, he mentioned that Gomez-Williamson is fine in terms of bit sizes. What about higher order relaxations for max cut? They're all fine, or just the first one?
I mean, if you're just trying to like optimize a polynomial subject to the constraints like xi squared equals 1 or xi squared equals xi, the discrete cube constraints, but you're trying to use higher levels of SOS, that's all fine. Those you can solve to like additive, exponential, and minus n to the d accuracy in n to the d time.
But the same cannot be said if I add the constraint at max cut equals 1 minus epsilon.
Right. If you try to say like the max cut is exactly 6,043 edges, we don't know how to like test feasibility or refute feasibility of that. Yes.
I think that there's some reasonable sense in which it is true that you can approximately solve degree d sum squares.
Okay.
I guess I would like to understand how it relates to what you presented. So I guess the way I'm thinking about it is in the dual side, where you try to find moments that are consistent with the polynomial equations that you have. And there, if you are in the compact sense, and I think what happens sort of in this case is that, so you have this little r and big R about the sum of square certificates. I think basically, because it's a dual, little r and the role of little r and big R switches.
Yeah, my understanding is that in the pseudo expectation side, like the little r becomes the problem,
Yes.
seemingly.
Then the little r, you can make it, you can sort of resolve the little r problem by saying that you only want pseudo moments that approximately satisfy the polynomial equations that you have. Relates to the comment by Thomas. And I think in that sense, you can approximately solve sum squares. Just that I think the issue is that about the primary, like the dual, like these dual things, then the notion of what it means to be approximately solving changes. And I think maybe the way you can solve approximately the sum of squares side is that instead of producing a certificate for the polynomial that you're given, non-negativity certificate for the polynomial you're given, you're producing a non-negativity certificate for a polynomial that is close. So that has similar coefficients.
Yeah, I mean, it's true that like if you switch to the dual side, you can find pseudo expectations or whatever that like almost satisfy all the constraints. But there's somehow, I think, a big difference between almost satisfying them and exactly satisfying them. I mean, if you've ever, and I know you have, like, constructed like an STP solution for something that like almost satisfies all the L2 squared triangle inequalities, and then you're like, well, now I want to fix it so it literally exactly satisfies them. It's not like so easy, right?
Like if you're doing that construction project and your errors are exponentially small, then usually it's not a problem, right?
Probably this is worth discussing at a later date, but yeah. Yeah, I mean, I'm only happier if like everything turns out to be fine.
I think the issue is really with infeasibility. Somewhere when you want to certify infeasibility of a system, that's when, in that world, there's no pseudo expectation that you can compute. If I give a three-side system and it's infeasible, you want to certify it's infeasible using sum of squares proofs, you're sort of stuck in this world where you find a solution, and then we don't have a.
So okay. I think what is that? If you use it for algorithms, right? Then you usually have some algorithm that sort of gives gets as input. Here you have a rounding algorithm that gets as input some pseudo expectations and then outputs as opposed to output a solution to your problem. And now now the question is does this algorithm depend on whether you satisfy the equations exactly or whether you satisfy them within exponentially small errors? And I think for the kind of rounding algorithms that we consider, or that we never sort of use the fact that you exactly solve the equations. And I think that so it means that also as Prasad mentioned, like these algorithms, they will produce a reasonable answer even if there's no exact pseudo distribution, as long as you have this exponentially good pseudo distribution.
I mean, I guess I would say is like this is something that like you have to check on a case-by-case basis and is not necessarily totally automatic. Like I think it's not inconceivable that you could be in a situation where it matters if you satisfy something exactly or merely very close to exactly. It could. I mean, I'm sure it is the case that like most of the time it's not a problem, but like I don't know a very compelling reason why it will never be a problem.
Questions or comments? Good. Great. Thank Ryan again.